Hi, Assalamualaikum. Today we are presenting our group project, which is vibration testing on a uniform cantilever. So, firstly, we introduce ourselves. So, my name is Muhammad Safwan bin Anuari, and my matrix number is 192074.
Hello, my name is Majid bin Norudin, and my matrix number is 192-562.
Hi, my name is Amelia Binti Juhar, and my matrix number is 191887.
My name is Darayani. My matrix number is 193846.
Hi, my name is Muhammed and Syazani. My matrix number is 192340.
Okay, thank you guys for introducing yourself. So, firstly, we present about the introduction. Go for the problem statement. So, for the experiment, we use the we will test about for the free vibration response. So, in free vibration, there is no force acting on the vibration system externally, such as the tuning fork after giving it some initial disturbance by striking it, the vibration in a swing after some initial back pull and simple pendulum motion. So this report leads to analyze the behavior of the system corresponding to vibration of the beam for different lengths and initial condition, in addition to determine the Young's modulus of the cantilever material. So the experiment is done on the uniform cantilever beam by attaching the accelerometer at the free end of the cantilever beam to measure the free vibration response. So the central position of this study is to make the vibrational response of a cantilever beam, thus adopting certain method that could help in making the calculation and comparing the results obtained from experimental with expected value. So there is 4 objectives for this project. Firstly is to plan and carry out vibration testing on a uniform cantilever. Second, to determine the lateral vibration of the beam for different lengths and initial condition. Third, to experimentally determine the Young modulus of the cantilever material. And lastly, to compare the expected lateral vibrations and Young modulus with the expected values. That's all from me. Thank you.
Okay, so I will continue with the theory, with the background theory. So we use the cantilever beam. So in this experiment, our cantilever beam is under free vibration. So the system consists of one end of the system refixed to support, and other side is to move that is free to move, that is known as cantilever beam. So the figure 2.1.2 shows the cantilever beam. So the cantilever beam under free vibration. Mitrovic 1960 state that for a cantilever beam that is subjected to free vibration, the system is considered as continuous system in which the beam mass is considered as distributed along the stiffness of the shaft. So the equation of the motion for the cantilever beam can be determined by using the equation number 1, and then the moment of inertia of the beam we can determine by using the equation number 2. So the cantilever beam under free vibration can be shown in the figure 2.2, and then the figure 2.3 shows the cross section of the cantilever beam that we use to determine the moment of inertia. So to determine the boundary condition, we use formula equation number 3 and number 4, and then the equation number 5 is to determine if when the beam is under free vibration, and then the mode shape for a continuous cantilever beam is shown by using the formula the long one, and then the natural frequency of the beam can be determined by using the equation number 7, and then the figure 2.1 for the first 3 under natural frequency and the mode shape of the cantilever beam that is under free vibration. So that's all for me.
Okay, so for me, I will explain about the expected value, which is static and dynamic. Static means that value that is the same, while dynamic is constantly changing value. Like we can see in the figure 2.21, we can see that the amplitude is changing. So the static deflection is formed due to the static wave. So we have the static deflection, which is F equal to K. So to calculate the dynamic value, we have to use the impact factor to have a good approximation of maximum dynamic value. So here we have the impact factor value, which is the upper one, and then we have the maximum dynamic deflection, which is from the static deflection multiple with the impact factor. So with the value, we can calculate the Young modulus. Okay, so as you can see in the box, we have all the static and dynamic value. So we can get the Young modulus value. So I assume to get the Young modulus value for each beam that we use, I assume that the value for K and the static deflection is same, so that I can get the expected value. So in the box, as the length of the beam is decreased, the expected Young modulus value is also decreased. But naturally, in real experiment, we will get the different stiffness of each beam and different value of static deflection. So I think I will pass up to Dayana.
So for the metallurgy part, first of all, we need to plan a flow chart first before proceed to the procedure. So first of all, we measure, we just plan roughly before proceed to the procedure. First of all, we measure the steel beam, a rectangular cross section. We choose a 3 different length of the steel beam, which is 60 cm, 100 cm, and 140 cm. And then we clamp one end of the beam with a length of the 60 cm at the beam support. And then we choose a transducer to measure the free vibration response. Next, we try an initial deflection on the beam, and we see that whether it allows it to oscillate. By applying the static force on the beam, we bend it from its equilibrium position. We also can the free oscillation also can be done by have a small tap on the beam, and then we plot the graph and record the reading in the database. Then we repeat the experiment with a different length of the beam, which is 100 and 140 cm. So that's all for the flowchart of the experiment, and then I will pass to the Danial to continue with the procedure.
Okay, thank you, Dayana. So for the detailed experiment procedure, the first thing first is we must choose and measure the steel beam with the width, the depth of 5 mm and width of 10 cm. Then we have a various length, which is 140 cm, 100 cm and also 60 cm. And then we clamp one end of the beam with a length of 60 cm at the cantilever as a cantilever beam support, which is free end at one end. And then we choose a transducer, which is the accelerometer, to calculate to measure the acceleration of the beam. Then, after we get the initial to give the initial deflection to the beam, we can apply by giving a force to the free end of the beam by touching it or put some weight on it. So for this experiment, we are choosing by applying the force by hand, which is about 4 cm from its static equilibrium position. Next, after that, okay, this will happen. Then the free oscillation occurs. Then we record the obtained data from the transducer and into the table below. As you can see below, there's a table downstairs. Yes, that's table. We record all the times with the acceleration. Okay, I think that's all for the detailed experiment. Then we have a few reference below. And I think that's all. Thank you.